Hello everyone, welcome to examples. We have example number 1, steel bar of rectangular cross section, this one, which is 3 centimeter by 2 centimeter, 2 centimeter horizontal dimension, and the vertical dimension is 3 centimeters, carries an axial load of 30 kilonewton. This is tension force applied at each end. Estimate the average tensile stress over a normal cross-section of the bar. This is a cross-section of the bar. It's normally 2 by 3. This is rectangular section, and the area is 6 centimeter square. So, in order to get the stress, it is a direct substitution, knowing that the stress sigma is the force divided by the cross-sectional area. The force we have is 30 kilonewton, and the area is 6 centimeter square. So directly we are dividing the force by the area. We are saying the force is 30 multiplied by 1000 to convert it into Newton, because it is 30 kilonewton, divided by the 2 by 3, but this is in centimeter, we make it by millimeter, so this becomes 20 and this is 30, so the area is 600 millimeter square. We are saying the normal stress is 30 multiplied by 1000 divided by 600, which is 50 Newton per millimeter square. The Newton millimeter square is megapascal. That's why our solution, the answer is the stress is equal to 50 megapascal. For the second example, 2 meter long aluminum bar where the modulus of elasticity is 69 gigapascal is subjected to a tensile stress of 175 megapascal. What is the most nearly the elongation? Either he gives 4 alternatives, either 4 millimeter or 5 or 8 or 9. We are utilizing the relation between the modulus of elasticity, which is equal to the stress divided by the strain. Here, he did not give the force, but in lieu of the force, he gets stress, which is the value of the force divided by the area. Knowing that the E is stress over strain, he gave us the modulus of elasticity, which is 69 gigapascal, 69 10 to the power of 9 Newton per millimeter square. The strain will be equal to the stress divided by the modulus of elasticity. Stress is 175 megapascal, which is 175 10 to the power of 6, divided by E, which is 69 multiplied by the 10 to the power of 9, which will give us 2.536 multiplied in 10 to the power of minus 3. This is dimensionless. In order to get the elongation, we have to utilize the equation of delta L over L is equal to the strain. So this value will multiply it by the 2 meter long, but we'll convert this length into millimeter. So we are multiplying this strain here multiplied by the length converted to millimeter, which is 2000. We will get that the elongation or deformation is equal to 5.07 millimeter. So the option which is near to the correct is option number B, because this value is most nearly equal to 5 mm. For the third example, determine the deformation of the steel rod shown in figure 2.9a under the given loads, where he gives the modulus of elasticity is 29 to the 10 of power 6 pound square inch. Here we have body which is consists of 2 sections, each section having different area. The first area is 0.9 inch square and the second one is 0.3 inch square, and is being applied by opposite forces. In order to estimate the deformation, we need to draw first the tension or normal force diagram. How we can draw this normal force diagram? We have this bar or composite bar is fixed at the end at part A. So our first step, based on the equilibrium of the forces, we have to get the reaction of A. Bearing in mind that the summation of the forces in the x direction is equal to 0, we have to assume what is the positive direction. We will assume that this arrow going from left to right, which resembles the tension, is our positive sign force. So we are taking the summation of forces at any point. Let us say at point A that the sum of forces should be equal to 0, especially the forces in the x direction, since we don't have any vertical direction, so we are talking about sigma f of x equal to 0. We'll assume the reaction at A due to the built-up support is toward from left to right towards the right. So we are saying that RA plus 75 minus 45 because it is going to the left plus 30 kips is equal to 0. We are equating and we are getting that RA is equal to, we send this 75 to the other right hand side, it becomes minus, and this will become positive, and the 30 will become negative. So this RA is minus 60. So minus, it means that it is opposite to the direction which we have assumed. It will be towards the left. We start to draw, starting from B, coming back to A. This is a tension force, and we will make this our datum line, and we assume that the positive value we draw it in the upper direction, and the negative one we are drawing it in the lower direction. So starting from here to here, we have a positive force of 30. So we can say that the normal force here is 30 from that point to that point, and its ordinate is constant until here. So it's being, this C is acted upon by compression force, which is 45. So before we have 30, we go down 45 in the direction of the negative, and we go from C to point B, where we met another force, which is tension of 75 kips coming in the positive direction. So we come up by the value of 75. Then from here to here, there is no force, so this force will keep going until it's finished with A. In order to check, this is a tension force. So sum of all these forces to the right hand side is from right to left, as being balanced by the reaction force, which is from right to left. It means that there is an equilibrium at point A. Once we get that force, what we need is the deformation of part AB, part BC, and CD. And we are going to get the summation of all the strains per part, as we can see in the following page. Part AB, this part, we have tension force of plus 60 kips, and we have area which is equal to 0.9 inch square, keeping in mind the relation that delta L over L is equal multiplied by stress over strain will give us the deformation. The stress over the original length is equal to delta L over L is equal to the stress divided by modulus of elasticity. So we are bringing L from the denominator multiplied here. Our length is 12 inch, and the stress is being evaluated from the force. So we get an expression that the strain, the deformation, is equal to PL over AI. The force is 60 multiplied by 1000, because 60 kips, as you can see, divided by the length, which is 12, multiplied by 12, divided by the area, which is 0.9 inches square, again multiplied by modulus of elasticity, which is 29, multiplied by 1, 2, 3, 4, 5, 6, 10 to the power of 6. We get positive deformation, which is plus 0.0278576 inch. And for the part BC, we have net force, which is compression, is equal to 50 kips all the way from B to C. So the deformation for part BC, we'll utilize the same equation, PL over AI, but here the force is minus 15 multiplied by 1000, multiplied again by the length, which is 12 inch, divided by the area. Area here is still 0.9, divided by 29, multiplied by 10 to the power of 6. It will yield to minus 0.006896, which is negative. We come to the last and third portion, is being acted upon by 30 kips tension force, which will yield positive deformation. So delta LCD is equal to the length of the portion CD multiplied by the force divided by the area, the cross-sectional area for that sector CD, divided again by E. Starting from the force, 30 kips, 30 by 1000 multiplied by the length, which is in that time is 16, divided by the area getting decreased, becoming 0.3, divided again by 29, 10 to the power of 6. It will yield positive 0.005174 inch. We make summation and we come to the final result, which is 0.07586, which is positive value. Thanks a lot and see you next time. Goodbye.